Okay, today's the second lesson on discrete probability distributions, and today's a special one. We're going to be looking at the binomial distribution. I found this quote from George Washington from the Hamilton soundtrack, but something he actually said, and I thought about it when I was thinking of like the possibilities of success and failure, and it's a nice quote because he talks about probability and just this idea of failure being based on some kind of probability. Um, Many applications in the real world revolve around success and failure. Is a product effective or not? Is a drug effective or not? Did it rain or not? Will the patient survive the next 5 years or not? In this lesson, you'll learn one of the most important probability distributions, the binomial distribution. So as a warm-up, there's a 70% chance that an allergy drug will be effective on a person suffering from the allergy. What is the probability that out of 10 random people, it is effective on 7 people? Um, so it, it's we kind of expect it to be effective on 7 people, but really, what is that probability that if you took a 10 person sample, 7 people are going to be effective? So the drug will work for those 7 people. Big idea hasn't changed. The learning goal is we're using the binomial distribution and expected values to model all probabilities of a possible outcome. We're going to be calculating expected value again. We're going to be displaying probabilities again in a table and a graph, just like the first lesson, but also solving probability problems that arise from binomial situations, and then making a connection between the sum and a very simple formula that we're going to find out. And you might have actually already thought of this formula here. What do you expect to happen? Binomial distribution requires what we call Bernoulli trials. Bernoulli trials are independent trials, and then based on success or failure. There's only 2 possible outcomes. That's what makes it a Bernoulli trial. So for example, if a drug's effective in 70% of the population, we call this a Bernoulli trial because it's either successful, effective, or failure, not being effective. And so success happens 70% of the time, and the failure happens 30% of the time. But also, it's independent. And so, really, if you found that it was successful on 7 people, it doesn't really change the effectiveness on the next person. We almost assume like infinite people here. We're not given a number of people that it's effective for. We're just given a probability of it. And so it's an independent trial. So what's the probability that the drug is effective in 7 people? We talked about cases. Case 1, it's effective in the first 7 people. We have slot method here that actually matters. And so if we think of the slot method, we have to think about each person being their own separate slot. And so if we have 10 slots, we can say it's effective on the first 7 and then ineffective on the last 3. And so this is one case where it's effective, but it's effective in the first 7. It doesn't have to be the first 7. Case 2 would be effective in 6 people in the first 6, and then the 8th person. And then ineffective in slot 7, 9, and 10. That's case 2. And then you realize that this is going to take a while because it's not just the first 7. You can also put the 7 slots anywhere in the 10. And so what is the value of each case? We can actually just use exponents to find the value of each case. So 0.7 to the 7 times 0.3 to the 3 will give us the value for each case. The question is, how many cases are there? How many cases are there? Well, really just answering a question from Unit 2. If you had 10 slots and you just needed to choose 7 people for the drug to be effective, that gives you the number of cases. Just 10 choose 7. It's the same idea. You've got 10 slots. You're just choosing 7 slots for this 0.7 to go into. So there's actually 120 cases. So if we take these probabilities, we're going to actually add them up 120 times, or take 120 and multiply by the probabilities, and we get 27%. You might be surprised by that number. You might have been saying, what? I expected it to be effective in always in 7 people. Well, that's just the case where you're effective in 7. In a similar manner, like you can try to do probability of 8, probability of 9, probability of 10, and see what happens. The formula looks like this. So you got this n choose r part, or n choose x part for counting the number of cases. So how many ways to do this? So how many slots do you have total? Which slots do you want the probability of success to go into? The p is going to be the probability of success, and the 1 minus p, which is like the 0.3 in that case, is the failure. N minus x is just the remainder after you pick the number of successes from a total. So this is actually a spreadsheet, and so I want to show you how to recreate this spreadsheet. So we're actually going to use this formula here. I'll show you how this is actually built. So what we do is we create a little table of values for x and p of x. We use little x for the individual ones. We go from 0 to 10, 0, 1, 2. And if it's too big, what we can actually do is highlight a few of them and grab this blue guy, and then it'll go to 10 ourselves. And then the probability is going to be our n choose r. And so out of the 10, we've got to do a combination. So we type the word combination, do brackets. And so we're going to do 10 comma 10 choose 0. So we want to choose none of them for it to be effective. Multiply that by, so we use the little star, 0.7 to the exponent 0, because none of them are going to be effective. And then multiply that by 0.3 to the exponent, and I'll just use a bracket, 10 minus 0, so which is like total of 10. And the reason why I use a cell, so I can just zoom in a bit here. The reason why I use a cell reference rather than just actually typing the number every time is because when I want to be able to just pull that down and for it to do that formula over and over again. And so what I'm referring to is this 0 here, but the next time it refers to the 1. And so you can see that the A3 changes to an A4. And then if we go all the way down, we can actually see that that was what we just calculated, 27% for 7. But you can see all your percentages. And then if you do like a little equal sum here, and then highlight what you want to add up, you can see that they add up to 100%. And we can make that like xp of x column now to get the expected value. You can say equals, multiply this by this, and again just drag that down. And so these are all our expected values, and then do the sum again of the expected values. You can kind of slow this down if you want to watch it again. And so it's 7. So we actually expect it to be effective on 7 people. It's just, and that's actually the most likely case, but it's distributed around the 7. And we can see that if we highlight these two columns, just highlight the X to there, and click Insert Chart, and it will kind of guess what chart you want. And that's not bad. We want a, like, we want not a line graph like that. We want a histogram or a bar graph. Bar graph is nice. So then that's how you actually recreate the bar graph of the probabilities. And so you can see that 7 is the most likely, but 6 and 8 and 9 are both likely as well. And so it's distributed around the 7. And it depends on the numbers how this distribution will look. But that's how you make the bar graph in a spreadsheet with the expected value chart and the table of values as well. So back to the lesson, you can see those tables of values here. The expected value formula, you actually might have realized that if you know it's a binomial, you can actually just multiply the 10 times the 0.7, and you get that it's effective on 7 people. And if you think about average, that kind of makes sense. Another example here is a study that came out in August 2017, just about sausages in Canada, finding that they're not really advertising the meat that's actually in the sausage. And so like they'll say that it's kosher and it's not, or they'll say it's pork and it's not. And so so this is just like an interesting question to ask. And so if you buy 20 sausages from the store, you can actually work through this. If we assume stats to be true, Calculate the probability 3 of the sausages don't have meat that's not advertised, and so 20% of them are supposed to, and so then we can use that, and then we create the chart, the bar graph, and then answer the question: what is the probability that at least 4 sausages have meat that is not advertised on the label? We can use the indirect method and then the expected value. And so the probability that 3 sausages contain meat that's not advertised, we use that 20% number. So out of the 20 packages, there's actually a 20% chance that 3 of the packages or 3 of the sausages are not going to have meat that's not advertised. The distribution chart would look like this, and so you can see the likelihoods drop off. So obviously you're not going to get 13 that aren't, but you could certainly get 4 or 5 that contain meat that's not advertised. The distribution graph looks like this, and so you can see that distribution around that 20% number, the 4, that'll turn out to be our expected value. Probability of at least 4, we use the indirect method, so we actually subtract the probability that we have 0, 1, 2, and 3. And we actually have all those numbers, so we just subtract those off, and we get 59%. 59% chance that at least 4 are going to have meat that's not advertised. Now, this is a big if, because this doesn't mean that your grocery store is going to have meat that's not advertised, but it was just a study that you can look up. And the expected value is n times p, which is 20 times 0.2, which is 4. Okay, so when to use binomial. So some examples when to use it, when not to. And so things that you can think about. So if you had something like this, so we know that 5% of people are afraid to be home at night. Would you use a binomial? 5 cards are drawn from standard deck. Would you use binomial? You're counting the number of hearts. 100 users or samples, so we find a certain percentage of marijuana-only users test positive for fentanyl. So they didn't know it, and that's true. And I didn't put a quote, I didn't put a percent. They just know that there is a certain percent. Out of 200 students in grade 12, there's 50 of them. They were surveyed, and 50 of them have reported binge drinking at least once a month. Out of 25 students, how many of them binge drink? Would that be binomial? And so the big thing you're asking is, are there Bernoulli trials, independent trials? Is that percentage changing every time, or is it the same every time? Drawing a single card from a deck of cards. You're drawing 5 cards from a deck of cards, one at a time with replacements, so you're putting them back. So you can ask, like, how is that different than number 2? Out of 30 car accidents, studies suggest 1 in 4 are caused by text and driving. So how many of the 30 are caused by text and driving? Spinning a spinner, counting the number of times you win after you spin 10 times. Playing Lotto 649, seeing how many matches you're getting. And then you've got a class who self-identifies female, like 15 self-identifies females out of a group of 5. So you want to count how many self-identifies females. Are these binomials? And so here's some practice.